Dr. Nick Gowland, Business Development Manager at the Graphene Engineering Innovation Centre, and you're watching the Challenges and Opportunities in Graphene webinar series from the University of Manchester. In this episode, we'll hear from one of our application managers, Dr. Liam Britnell, on some of the issues around recycling and end of life for graphene products, and how understanding the whole system approaches to the supply chain can offer opportunities for both sustainability and for profit. Today we have Dr. Liam Britnell giving this webinar on the environmental impact of graphene and opportunities in sustainability. So Liam got his PhD from the University of Manchester in 2012, and he followed that by managing R&D at a startup graphene and graphene production and applications company. He then rejoined the university in 2017 and is now an application manager at the Geek for the printed electronics lab. But as you'll see through this talk, he's very much an all-rounder and very good generally, I think, on graphene and graphene commercial applications. So on that, Liam, I'll hand over to you. Please share your screen. And as I said before, if there's any questions, please write them in the chat and I will pick them out through the talk to give to Liam. So yeah, enjoy.
Well, first thing to say, thank you so much to all of you for joining. I think it shows that this topic, is increasing in understanding, and it's of increasing importance, clearly. But I guess the first thing to say is that environmental sustainability is something that the Graphene Engineering Innovation Centre is taking very seriously. Of course, it's a subject that doesn't need much in the way of motivation. The very real impacts of climate change, of course, that we're seeing, and other effects. But there are sort of specific themes at the Geek which have, I guess, prompted us to have a greater look at this, particularly in my area around printed electronics. If we think about things like recycling of e-textiles, we can do this, start thinking about how we're going to recycle potentially, plastic packaging that might have graphene and various things in it. So those are the sort of crux where it comes from. I think there's far more than I can reasonably try and cover here, particularly on the areas where graphene potentially has benefits, and I think those are the things that we probably focus on a lot in any case. So I'd like to also have a look at sort of the background to some of the impact, perhaps in another sense. And generally, we're seeing biggest benefits or big benefits where graphene is used in small quantities. That's one of the small mass volumes. That's one of the things we see as a big driver, and particularly increasing lifetime of products through better durability, reducing the amounts of other materials needed, and potentially replacing or removing the need for hazardous or more harmful materials to extract. So let's start by defining what we mean by sustainable development. So sustainable development is that which meets the needs of the present, it's a typo, without compromising the ability of future generations to meet their own needs. So that's quite nicely captures the sort of premise of what we're trying to achieve here. And what it means is that we really need to understand the intricate nature of a wide range of sectors, industries, and kind of the interplays between them. Of course, it's going to require action on multiple fronts. So not just technological advances, but changes in social practice and behaviour, and given quite some different prominence by this United Nations 2030 Sustainable Development Agenda, which has 169 targets across 17 goals. And I think we can quite safely make the argument that advanced materials has a role to play in achieving many of these. And I'm sure you've heard before, news stories or articles around innovations with graphene in things like water filtration, clean energy, lowering the infrastructure impact of infrastructure and so on. But I think a key message I want to get across today is that applications where graphene can increase durability, like the lifetime of our products, are particularly key in this reduction of impact, and also where we're able to lightweight materials in the sense that we're removing the need to use so much in terms of mass and things like structures. And I think because of this fact that we need to take perhaps a holistic approach, and it's something I know sort of Mike Shaver is approaching this from multiple angles. Really needs sort of interdisciplinary and collaborative work to kind of maximize the potential here. So just first thing to say, I guess, is that sustainability is kind of already built into the core research themes of the Geek. So if our goals in membranes, for example, are to create cleaner water with less energy expenditure, we're going to be likely to have a net positive. If the goals in composite materials are to reduce weight of structures at the same performance, we're going to reduce depletion of raw materials, reduce transport emissions, and so on. And again, that's going to be a positive. And if our aims in batteries are to improve, storage capacity, lifetime, similarly in coatings, if we're looking about, prolonging the life of perhaps metal structures, preventing corrosion. So all of these things are going to have net positive. But I think one of the key things I wanted to get across today is that, there's a layer of detail behind all of these developments. In terms of the industrialization of this, the practicalities of what's going to happen at end of life, material sourcing, and so on. And we really need to have an understanding of this to judge the impact and the relative benefit of using graphene in the way we're intending to. And I think it's particularly prescient now as we're really starting to see uplifts in the volumes of graphene used. I'm not going to talk at all about REACH today, but obviously REACH registration is an also important fact here as well. So for the purposes of this discussion, let's just start by imagining a situation where graphene products are found with ubiquity in the marketplace, as a component in a variety of products. So the first thing we've got to ask ourselves is, what's the impact of that going to be on the environment? And we use that in both, the sense it's commonly used here as a negative impact, but also as a positive impact, of course. So we'll address this first with a look at sort of graphene production processes. And then I want to have a look at what the sort of typical application spread is for these sort of graphene type applications, because that to some extent is going to determine how they're going to reach end of life, when they're going to reach end of life, and sort of what through channels they will reach that. And then, particularly with a focus on polymer composites, I want to have a look at what the particular challenges might be around recycling, and then finish up by looking at opportunities, particularly ones that we're heavily involved with currently. So we come first to how graphene is going to impact the environment. So first thing to remember is that all the processes in the production of a product need to be understood to determine this level of this impact. So this is life cycle analysis or some variant thereof. We'll be using that term a couple of times in this talk, so it's probably helpful to think about that. So we have this simplified example. So let's assume that graphene's being made from natural graphite that's mined and obviously has some impact on the environment. This needs to be transported to some production facility, powdered, exfoliated, potentially combined with other materials, each of which is going to have its own impact. And we're going to finally produce some product of some form. And this will obviously be then transported to a customer or end user, and finally disposed of in some way. So I guess the important thing to consider here, and we'll look at this on the next slides, is the multiple threads that this brings together. And this can become, even at a high level, quite a complex system. And we're going to look at that particularly with a view to graphene production first. So there's a few terms of reference that might use in this talk, or you might read elsewhere, which is cradle to gate, usually referring to the beginning of this process, the extraction of materials through to some sort of semi-finished product, sort of pre-consumer generally. Cradle to grave, where we're talking about the lifetime from extraction of materials to disposal, and then in the circular economy, this idea of sort of cradle to cradle, particularly if we're looking at sort of a closed loop recycling system where we're sort of striving for infinite reuse of materials without loss of properties. So let's have a look at sort of a hypothetical example that is based on reality at least. But so let's suppose we have some process to produce graphene, and we want to make a graphene printed heater onto fabric or something that we're going to sell in India. So So if we surveyed graphite mines, graphite suppliers, we found one in Brazil that's can supply the right grade of graphene at the reasonable cost. Have that shipped to the UK where we're doing graphene production, combine it with additives, perhaps viscosity modifiers and so on from perhaps a German company. We'll then ship that quantity of ink to China, print it onto into place with electronics and power electronics and everything, and finally that's shipped to a consumer in India. So I guess the point really I'm trying to make here is this is necessarily quite a complex system, lots of variables. Each process in this system is going to consume energy with some efficiency. It's going to produce some waste, whether that's in the form of yield losses, solid waste, liquid waste, and we do really need to can think about this, particularly when we're talking about scaling up. And we really need to consider, when we're looking at these performance improvements in, say, things like durability and so on, we kind of need to balance this against the reality of producing it. So, I mean, the great news for graphene is that a lot of cases we are focusing on that, improving durability. That's going to be a driver for environmental savings, and so on. But probably key to also point out is that this is going to be heavily dependent on the time in which it's done. So, for example, if a process is getting more and more efficient over time, of course, that's going to give us savings. And that's particularly key for new and emerging materials, things like 2D materials, which for the most part, the process has not been optimized. Most haven't been scaled up. We've not included things like energy recovery or material recovery in those processes. So it's also going to be dependent on where in the world these steps are happening. For various reasons, but one very simple one is the makeup of energy, electric supply. It's going to vary from country to country, different levels of renewable resources and everything used. So if we just think about this life cycle analysis in a bit more detail, so because we'll use it for looking at the graphene production processes. So the first thing to say is underpinned by this ISO 14040, and obviously you can find more information about how these things how these analysis is performed in accordance with that there. So it's a tool that's used to support, and it's probably key to emphasize, support environmental decision making, environmental strategies, business planning, and you see that the likes of BASF and General Electric reportedly use it quite widely in their sort of strategic planning purposes. So it's often used as a comparative assessment tool. Used for perhaps looking at cleaner technologies, and I've also picked out here sort of thinking about unintended consequences, and it can help to tease out some of those as well. So introducing a process that prevents use of toxic materials, we need to understand whether that has knock-on impacts, and so on. So typically the outputs are things like global warming potential, material depletion, anything that's deemed harmful to the environment, and depending how this is done, there might be 10 or 12 of these outputs, each of which is given some significance in the analysis. And these kind of analysis are not without critics either. So some of the limitations, the data that we get out is only going to be as good as the data that we put in. Data gaps, inaccurate assumptions, and so on are going to lead to inaccuracies and uncertainty. And this is particularly present for something like graphene, where we don't have databases of different production methods for graphene built into the kind of software that do these. Of course, this all needs to be balanced against what is financially viable, because that's what's going to drive a lot of these things. And as I've said, complex calculations that require sort of dedicated software, and also experienced people to interpret the results. So so and the last point I'll make out is just a note of warning, really. I mean, it's very easy to sort of try and compare numbers from different studies that are done on this, and of course, without a sort of understanding of what the goals or the scope of these original studies are, it's very easy to make sort of apples to oranges type comparisons. So I think that the points to really make sort of take home messages here. So we need an understanding of this whole system, not just our part within it, whether that's as a producer of graphene or a component producer. And we need to think about these knock-on effects. And I think it's also an opportunity as the graphene community grows to think about how we can effectively sort of share data in a sort of transparent fashion to make these kind of decisions.
Liam, can I just jump in there on that previous slide? I mean, Mike Shaver made a good comment. Mike, would you want to just expand on that comment? Because I think it's quite a useful one about life cycle analysis. And
yeah, I mean, I think it's even if we look at the plastics industry, there's a lot of debate in terms of the quality of LCA, right? You can choose your metrics to make something look good or make something look bad. And so if you guys look at sort of plastics and packaging, there's a lot of work now at evolving what it means to compare two different end-of-life pathways. So a robust thing versus something that's easy to recycle. And so there's a number of groups within the UK and actually in the US as well that are kind of developing those things. So don't just limit yourself to ISO 14040, but take advantage of the fact that really the UK is leading in this space at developing next generation LCA tools. But you are completely correct that it's a systems approach and it's underpinned by open data. And so it requires companies to actually be honest about what they're doing.
Thanks, Mike. That's a very, very salient point. Yeah, and particularly from the point of view of Geek, we're very keen to work closely with people like yourself and other institutes that are can do these understand these types of analysis well. So I'll just jump on to the next slide. So bearing what Mike's just said in mind, let's look at a particular example of this. So it's a couple of years out of date, and generally there isn't a huge amount of published literature on these kind of things. This is particularly focused on the sort of cradle to gate, I guess, production of graphene. Perhaps some of the uncertainties about end of life are less important here, but nevertheless, let's bear that in mind. So this particular study looked at frozen in time processes. Frozen in time, I mean, they're a couple of years out of date now, perhaps, looking at oxidation reduction, electrochemical exfoliation, chemical vapor deposition. And I want to emphasize, I think this is quite key here, that I'm not suggesting for a minute that we're using these kind of numbers to determine the type of graphene we should be using in any particular application, because we know that those are going to be determined by the type of graphene. The properties we'll get in application will be determined by the type of graphene and its process. So simply trying to minimize these numbers is not really a game that we want to play. But I guess the point I'm trying to get across here is that we at least need to have some basic understanding of this in order to make comparisons. So if you look, and I guess the other thing I want to, perhaps apart from the bare numbers, is really looking towards the trends. So of course, as we scale any of these processes from a lab scale up to a commercial scale, we're going to see improvements, particularly improvements when we look at energy intensive processes. If we're talking about reducing or moving towards sort of renewable sources of electricity. And the other point I should put out here is that the same study looked at not just the global warming potential, but a raft of, I think, 12 or 13 other things like acidification, eutrophication, and in comparison, these are all minimal in comparison. So have been sort of excluded from further thought. So we should really be only interested, as I said, what's happening perhaps at the commercial scale, and we'll have to take into account the uncertainties in those predictions. And again, I think this is just building on that point that a lot of this data is locked away inside companies. And to make real value judgments, I think we need to think about how we can perhaps look at opening that up. Generally speaking, nanomaterials typically going to have larger impacts than bulk materials, just as a very broad statement, because of the level of processing, sophistication of processing that's required. And I'm not sure we should expect necessarily to match other bulk materials. But the other thing to remember, of course, we're using these typically in much smaller quantities, perhaps a few weight percent. And if we can generate a product that's lasting 50% longer, using 50% less material, it's quite clear that we can, or it is clear that we can obtain a net benefit. So with that in mind, I just wanted to emphasize that again. So nanomaterials typically going to have, if we look at the range of nanomaterials, nanosilvers, carbon nanotubes, etc., we see that it's quite common to have high impact. Production is also only part of the story. So benefits in performance improvements, which mean that we get longer life or increased durability, smaller material usage, so on, is obviously going to be worked up against this. And we really need to work together to sort of build up a representative picture that's sort of true and accurate.
But take advantage of the fact that really the UK is leading in this space at developing next generation LCA tools. But you are completely correct that it's a systems approach and it's underpinned by open data. And so it requires companies to actually be honest about what they're doing.
Thanks, Mike. That's a very, very salient point. And particularly from the point of view of Geek, we're very keen to work closely with people like yourself and other institutes that are, can do these understand these types of analysis well. So I'll just jump on to the next slide. So bearing what Mike's just said in mind, let's look at a particular example of this. So it's a couple of years out of date, and generally there isn't a huge amount of published literature on these kind of things. This is particularly focused on the sort of cradle to gate, I guess, production of graphene. Perhaps some of the uncertainties about end of life are less important here, but nevertheless, let's bear that in mind. So this particular study looked at frozen in time processes. Frozen in time, I mean, they're a couple of years out of date now, perhaps, looking at oxidation reduction, electrochemical exfoliation, chemical vapor deposition. And I want to emphasize, I think this is quite key here, that I'm not suggesting for a minute that we're using these kind of numbers to determine the type of graphene we should be using in any particular application, because we know that those are going to be determined by the type of graphene. The properties we'll get in application will be determined by the type of graphene and its process. So simply trying to minimize these numbers is not really a game that we want to play. But I guess the point I'm trying to get across here is that we at least need to have some basic understanding of this in order to make comparisons. So if you look, and I guess the other thing I want to, perhaps apart from the bare numbers, is really looking towards the trends. So of course, as we scale any of these processes from a lab scale up to a commercial scale, we're going to see improvements, particularly improvements when we looking at energy intensive processes. If we're talking about reducing or moving towards sort of renewable sources of electricity. And the other point I should put out here is that the same study looked at not just the global warming potential, but a raft of, I think, 12 or 13 other things like acidification, eutrophication, and in comparison, these are all minimal in comparison. So have been sort of excluded from further thought. So we should really be only interested, as I said, what's happening perhaps at the commercial scale, and we'll have to take into account the uncertainties in those predictions. And again, I think this is just building on that point that a lot of this data is locked away inside companies, and to make real value judgments, I think we need to think about how we can perhaps look at opening that up. Generally speaking, nanomaterials typically going to have larger impacts than bulk materials, just as a very broad statement, because of the level of processing, sophistication of processing that's required. And I'm not sure we should expect necessarily to match other bulk materials. But the other thing to remember, of course, we're using these typically in much smaller quantities, perhaps a few weight percent. And if we can generate a product that's lasting 50% longer, using 50% less material, it's quite clear that we can, or it is clear that we can obtain a net benefit. So with that in mind, I just wanted to emphasize that again. So nanomaterials typically going to have, if we look at the range of nanomaterials, nanosilvers, carbon nanotubes, etc., we see that it's quite common to have high impact. Production is also only part of the story. So, benefits in performance improvements, which mean that we get longer life or increased durability, smaller material usage, so on, is obviously going to be worked up against this. And we really need to work together to sort of build up a representative picture that's sort of true and accurate. So I'll just move on to the next bit. So looking at sort of what the diversification of applications is, what that might mean for end of life. So I've just put up here a pie chart taken from a recent sort of market study on the demand for graphene in 2020, done by sector. And it's a little bit difficult to make predictions about what's going to happen to graphene at the end of life when we have such a breadth of applications. And there's still a certain amount of uncertainty about what the market adoption is going to be in any of these sectors. But if we try and simplify it, if we think about something like a closed loop recycling, where we have a good level of segregation from other waste streams, materials generally reformed into sort of similar or same products with similar material properties. An example being something like glass, a simple example. But again, the sort of segregation from other waste is going to be key. You can also think about something more like an open recycling open loop recycling, where typically there's going to be a greater mixture of materials, and often in most cases the materials are recycled into an inferior product in terms of material properties. So I guess closed loop recycling, perhaps Mike may disagree, I don't know, is sometimes seen as the holy grail of recycling. So the idea being that we can reuse material without the need to introduce virgin material to maintain those properties. And one particular key challenge we're going to look at is the segregation of that waste. So if we look at the distribution here, we can make some very, very broad attempts at judging how this might look. If we split this into two parts, so the blue is signifying perhaps applications that have a higher potential for being segregated, and red, lower potential. So focusing first on the blue ones, there's a lot of effort still ongoing to try and ensure that we can effectively recycle things like batteries. But I think for sure, increasingly, these are going to be segregated from other waste streams, and we see increasing regulation there. On the other, we have other materials like anything that's things that are built into consumer electronics, like transparent conductive films or logic, etc. That's going to be handled segregated fashion, as is sort of water filtration, tires, and so on. So there's a good chunk of applications there, and that's good because it means there's some chance that they will be go into a stream that's going to be handle them appropriately. But we also still have a chunk of applications which are going to be generally mixed in with other materials, perhaps ones that are deemed to have sort of lower value. So I want to have a look then, if we think about how that is going to then impact how they will, the routes by which they'll sort of come to end of life, and have a particular focus on polymer composites, because I think this is quite relevant. Generally speaking, I think it's true to say that composite materials are generally quite challenging to recycle. So we're intentionally, in a lot of cases, trying to make them tough. They're by nature sort of non-homogeneous. Multi-materials typically are harder in things like packaging to recycle. And we need to think about what the sort of current practices are in place for handling plastics. So perhaps the simplest fashion is mechanical recycling, where you have shredding, sorting, perhaps by color or polymer type, remelting and re-extrusion into a new product, again, usually with a lower grade application. Whereas something like chemical recycling refers to a process where we might be breaking the plastic down, either through use of solvents to obtain a solution or some catalytic or thermal processes to obtain monomers. And these can be, in principle, then cleaned up, repolymerized into new materials. So with that in mind, let's just think about two options. So what the options are going to be for graphene nanocomposites. Perhaps
quickly before you move on, a couple of people have asked what you meant by logic on that previous slide.
It's just really referring to things that are built into computer architecture. So, transistors, something like that, for example.
Cheers.
So with that in mind, let's think about sort of two options we can have here. So this is outside of the idea of biosourced or biodegradable material. So I guess the first overarching point I wanted to make was about releasing to the environment. So I think there's still a good amount of debate about what the true toxicological effects of graphene are in the environment. But I think we can follow the sort of precautionary principle that until it's deemed safe, err on the side of caution and prevent unnecessary release into the environment. I guess the next is whether graphene is going to be treated as contaminant in these waste streams. And of course, it's going to have an intrinsic value in the original application we're using it for, otherwise we shouldn't be using it. But once we have it in with a mixture of other materials, is it going to be treated as contaminant? It's going to potentially affect coloring, it's going to affect mechanical properties, it may behave in unpredictable ways with other materials, other contaminants there. And therefore that leads to a very real chance that these things will end up in landfill and incineration. But can we do better? So I think the issue of sorting black plastics more generally is not something I'm going to get into, but rather there's interesting developments at the University of Manchester around using a graphene-based sort of optical system to improve sorting there. But if we're assuming that we don't want graphene to enter that waste stream, then I guess we are left with two options. So one is to ensure proper segregation of waste, which means focusing on, in the short term, on applications where we can readily segregate graphene waste from other products. These might be the ones that have potentially higher value, longer life applications, and already treated differently, things like automotive recycling, for example. And then perhaps in the longer term, work towards a technological solution like tagging of products. I know this is something that Mike's interested in a sort of reliable and viable way to sort them. And I think that for some this might sound unrealistic, but there is good progress in packaging industry, in sort of industry-wide collaborations, looking at sort of smarter automated sorting systems, using things like chemical tagging, digital watermarks, and so on. And this is sort of part of the growing trend of producer responsibility. And I think as people involved in the graphene supply chain, we should think about this. And if we can justify the use of graphene based on its performance improvements and its reduction of impact generally, then we can work with those technologies to ensure that we sort of mitigate the end of life impact. So I guess in addition, that's going to lead me then to my next point, which is keeping graphene composites separate from other materials is perhaps something that we should be striving for in any case. So if we consider how much time, effort, resources is gone in and will continue to go into getting just the right graphene into just the right matrix, in order to maximize the performance benefits, we don't want to lose that at the first recycling step. So I guess the other option is to put a stronger focus on use of graphene in plastics, which might be more amenable to some form of chemical recycling. Again, where we're sort of depolymerizing the plastic back to a more basic form. We can think about removal, recovery of graphene more easily than we can from a melted system. And we can also think about preventing graphene getting into other plastics and causing greater wastage. So I think these are both options which retain as much value in both graphene and the constituents and the host matrix as possible. So I want to just jump then after looking at these messages, after these take-home messages. So composite recycling is notoriously challenging. I think we need to focus on processing materials which retain the value, and segregation of waste is going to be key to that. So I just want to jump now onto some of the opportunities which we're involved with. So this first diagram is something that you may well have seen commonly before. So it gives us a sort of hierarchy of options to reduce impact, the ones at the top being most favourable. And if we're starting with the elimination of use of harmful processes and materials, if we can't do that, then we look at minimising them and so on down the chain. So there's a myriad of examples for each of these, certainly at the top with graphene, but the ones I want to focus on are around minimization of material and recycling. So, right at the top of the list, we've got there lightweighting and increased durability. So lightweighting, by that I mean sort of reducing wall thickness of materials, reducing the mass, and this is going to have then benefits on impacts in terms of material usage down the road, reductions in transportation costs and so on. And durability then should also be another key aim. So if a product's lifespan is increased, we're also going to reduce the amount of material that's needed to be fresh material that needs to be put into the supply chain. So we also see a number of projects looking at converting waste streams into graphene. So this helps to minimize extraction of new materials, raw materials. There's a paper by James Torr's group last month showing that wide range of waste streams could be turned into graphene with flash pyrolysis, and I believe that's being commercialized. We also have an ongoing project with a company looking at turning waste from mining into a more suitable application in cleaner technologies such as batteries. And similarly, the university has projects in sectors like oil and gas looking at converting those waste streams as well. We've also supported a number of companies looking at using graphene to bring the properties of recycled plastics back close to or even above properties of their virgin plastic counterparts. And while this doesn't necessarily reach the goals of a closed loop system, it can help to reduce impact through reductions in material depletion and so on. So just a few sort of more specific examples. So the first one, which I think is a good example of a combination of lightweighting and durability. So generally, it's a growing area of interest, the use of graphene in construction materials, here particularly in concrete materials. And we work closely with a team at the University of Manchester and commercial partners looking to drive these developments forward. So we know concrete generally is a big contributor to global warming, and with those impacts primarily coming from the production of the input materials and also quite significantly transport of those materials. So, I mean, there have been multiple studies, I think backed up by also by research that we've done internally, found that we can see improvements in these key mechanical properties through modifying this sort of microstructure and these aggregates. Various studies have shown improvements in tens of % improvement in tensile strength, compressive strength, flexural strength, but also improvements in abrasion resistance. We can see that graphene has this tendency to sort of fill micro cracks and improve this interface between sort of larger aggregates. Can also reduce water ingress, reduce chlorine migration, and these can also lead to premature failure. So we have quite a few things going in our favour here. So we're using potentially less material up front, and that's going to have a big knock-on effect on the level of materials needed, obviously, and the transportation of those materials. And if we can really make use of that improvements in durability in terms of corrosion resistance and so on. generally we're going to have reduce the overall level of materials and energy that goes into maintaining and rebuilding these structures. I think generally we've seen this as an area that's certainly increasing in interest. We've seen that, you know, for quite large infrastructure projects, there's a increasing focus now on whole life costs, not simply upfront costs. So this is an opportunity for materials like graphene, which might struggle against commodity materials on an upfront cost basis. But when we consider the benefits over the lifetime, it becomes much more beneficial. We have ongoing projects with partners in this area. So a couple more examples. So we, where graphene is being used more as again, as a sort of filler, but perhaps in upcycling of recycled materials. So the first on the left relates to what was really spurred on by this sort of severe housing shortage that we have in the UK. And the government set some quite clear targets to the construction industry in general about reducing costs, building faster, lowering emissions, and so on. So with that in mind, last summer we ran a study which hasn't been published, but we were basically comparing the use of graphene in recycled polymers to virgin plastics, to other conventional building materials, looking at some elements of life cycle assessment, looking at the panels designs for modular homes, doing sort of engineering calculations, looking at thermal efficiencies and structure and so on. And we really wanted to understand what sort of the availability of these recycled plastics was in the UK, and the use of those in sort of potentially long-term sequestering of that in structures, and simultaneously solve sort of societal housing challenges. So taking what otherwise might be waste going to landfill, we've begun designing a sort of multifunctional panel structure to use as a building block for building homes, with the aim that it would be sort of swiftly assembled and installed with sort of the level of functionality that we sort of require in modern homes. And we saw that there were significant reductions in emissions and costs versus the comparative tools. So we're building on that, looking at sort of supply chain, really trying to verify and qualify those initial results, and looking to sort of high throughput manufacturing techniques, and looking to partner with people on that to take that forward. So the other side we have here is looking at sort of carbon black in elastomers. So this is an area again that seems to have a lot of interest for graphene. A number of published papers looking at lower rolling resistance, improving wear resistance, and so on. Typically, tire rubber has a lot of reinforcing fillers, carbon black, silica, and there's a lot of work going on to try and replace those and try and maximize those sort of key performance metrics. But there's very little in the way of published life cycle analysis around this. So, yeah, while there are reports up to sort of 23% reduction with replacement of wholesale of carbon black with graphene, that's certainly something that needs to be built on to understand the real benefit. We also consider what happens at the end of life. So, of course, tires are made from vulcanized rubber. We can't just sort of melt them down, but for what we've seen, there's quite a lot of work ongoing in attempting to use sort of selective devulcanization to again bring these rubber materials back to something that can be cleaned up more effectively and reused in higher grade applications. And we've been working with a company looking at use of sort of ground rubber with addition of small amounts of graphene to replenish and rejuvenate those mechanical properties. So I don't know how I'm doing for time, Nick. Like,
fine,
okay,
carry on. You nearly done, aren't you?
Yeah. So I just wanted to say what the Geek's doing about this. So I think there's been over the last 6-12 months, there's been a sort of increasing understanding that we need to shift a stronger focus towards sustainability, particularly in helping the community as a whole on some of these sort of grander challenges and particularly around sort of this transparent data sharing and so on. So we're running, as I've already mentioned, internally and externally funded projects, with primary outputs being sort of sustainable development goals, promoting sustainability within projects, offering support. We will be on sort of reducing impact, perhaps running some of these types of analysis as we've discussed here. We'll be nominating a sort of sustainability champion within Geek to try and lead some of these ideas forward, and collaborate with the Henry Royce Institute and others. And perhaps Mike want to say a little bit about a new hub that is recently announced in Manchester in this regard. And just finally, some take-home messages. So I think, clearly many opportunities in sustainable development graphene, far more than I focused on here. I could have spent the whole half hour or 40 minutes on that. But I think the key is really thinking about the end of life at the sort of conceptual stage. So trying to design durability and recyclability into products from the very beginning is key, not as an afterthought. We really need to think about this as a whole material system and not just our system in isolate, our part of the system in isolation. Collaboration and transparent data are really, I think, where the community really needs to start getting to, as quantities of material produced and sold are increasing. And I just wanted to focus on, we need to look at how waste is segregated, whether it needs to be, and how we can retain the most value in graphene and the other materials from doing so. So I think that brings me to the end. So I'd like to thank you all very much for listening, and I hope it was interesting.
Thanks very much, Liam. Really good. Before we go to questions and before we get a comment from Mike as well, could you just go back to your slide about the Geek? I was just going to offer James Baker, the CEO of the Geek. I was just giving him a chance to add to that, James, if you have anything to add.
Thanks, Nick. No, thanks, Liam. Thank you, everybody, for attending. Just really to build on what Liam said, that I think sustainability will be a key theme, particularly as we come out of the current pandemic around COVID-19. I think looking at local supply chain, looking at recycling, looking at the total carbon footprint. And as Liam just gave in a couple of examples, I think sustainability, could increasingly become a differentiator in terms of products and applications. So really just keen to follow up and talk to people around that. What's the opportunity from reduction in material, improving productivity, through to lightweighting, reducing carbon footprint through less fuel, less emissions, etc. So yeah, thank you, Liam, for the presentation, and keen to follow up and see how we actually might build a community. Also mentioned through Professor Mike Schaefer and the Royce Institute, they do have a sustainability theme, as well as the large corporations. We're also looking to work with small businesses, not just in Greater Manchester. So yeah, sustainability for me will be a key theme going forward. So keen to follow up and try and build some momentum in this area. Thanks, Nick.
Cheers, James. Mike, you got anything to add on Liam's presentation or any specifics about Royce or any of your work?
Yeah, so I guess a bit of a clarification in terms of my role. So I have a role within the University of Manchester in terms of being a professor of polymer science, but I'm then the sustainable materials champion or challenge lead, or they keep changing what they want to call me, for Henry Royce. And we've just announced the £10 million center that's called the Sustainable Materials Innovation Hub. And actually is sort of like the sustainability version of Geek in terms of being quite industry focused, but being certainly focused on providing advice and assessment in terms of evaluating sustainability. My dogs have taken to right now to being monsters in the background. So I think what's really interesting here is that because you've got this expertise from graphene and sustainability in one place, you can be quite smart about it, right? It's really interesting to think about what opportunities there are to providing more sustainable materials. Sammy, shut up. And like that's especially true when you think about what is going to change in waste management around the world, and certainly what's changing in terms of our views of materials. So does graphene, for instance, I have no idea, does graphene provide robustness that actually allows you to make more sanitizable structures that still maintain reuse? We're going to get into a post-COVID world where everything has to be cleaned if we're going to have that be robust. And are there opportunities there to look at different properties or different ways we can treat materials? Because it is extending that lifetime and extending the amount of time you have in circulation that provides opportunities. Still needs a plan at end of life, but it's a very different plan and can be a more expensive plan.
Thanks, Mike. Really nice comments. Any questions? Please put questions in the chat, or to some degree shout out. But you know, if you can just put your name in the chat, I can call you. We did have a question from Ivan Buckley, who's the Director of Business at the Geek. Ivan, do you want to put your question to Liam?
Yeah, thanks, Nick. Thanks, Liam. Very good. Yeah, my question really is, and I guess Pietro Cataldi and Mike Shaver might be able to answer it as well. You talked about land disposal, Liam, and I just wonder, was there any indications as to the time it takes for graphene to be biodegradable within a landfill? Is there any indication of timelines? Also, if it doesn't go to the landborne waste sites and it goes to water, is there a difference as well as to how long it takes to degrade?
Liam, you talking about it. Go on. Sorry.
Yeah, sorry, I was just on mute. I don't have a number in mind, I'm afraid, Ivan. I think from my understanding, you know, it's not something that is going to, let's say, biodegrade in a normal compost environment very quickly. You know, it survives. You know, we don't see it being eaten in most cases by the sort of bacteria that you know, that break down other sort of natural things. So, but I'm afraid I don't have an answer on the timescale for that.
Pietro, do you want to make any
comment? There are some reports that, for example, from Bianco, that basically state that graphene oxide can be decomposed by enzymes in some specific case. So yeah, it is not compostable, as you said. It is not like water soluble. It is not, but it can be decomposed by some particular enzyme. Yeah, I mean, of course, I mean, recycling is one stuff. Another stuff is, of course, to withdraw a material after use in the environment. And then, unfortunately, this is happening also not on purpose. And there is the chance that, for example, let's say a material which is made with a biodegradable, a composite which is made by a biodegradable material, which is reinforced with graphene, could, for example, last more in the environment because of some barrier properties of graphene and these kind of things. On the other hand, I would say that if you can obtain similar properties with a bio-based material compared with a, let's say, petroleum-derived plastic, it is still worth to use the material that is bio-based, because you are reducing the environmental impact of the production of the material. So I mean, there are many, let's say, parameters, in my opinion, that should be considered.
Yeah, nice point, Pietro. Thank you.
I just want to just be a little bit cautious there. So almost all bio-based polymers that are on the market right now have a significantly higher carbon footprint. So if the argument for incorporating graphene is to reduce the carbon footprint, bio-based materials actually have a more complicated end-of-life option and a higher carbon footprint right now. And so just because something is bio-based, it still actually points to the same thing that Liam was saying. You have to take a critical approach and evaluate it.
Yeah, so probably is a question of volume of production, right?
It's significantly higher for all bio-based polymers that are on the market right now.
Yes, but isn't it related with the volume of production?
Yeah, but you can't. Then you come down to source, right? And you have a global population that can't eat with our current agricultural output. So.
Yeah, I understand your point. Yes.
I mean, this is interesting. I'm sure we could have another hour of conversation on this, which will be useful. I'll just point everyone to the comments very quickly. David Hilton from Midas, which is the Manchester Inward Investment Agency, they're running a sustainability and innovation webinar on the 10th of June, which Professor Mike Shaver is also speaking at again. Busy guy. If anyone's interested, please email David. His email's in the chat now. We also had a question from Adrian, I believe. Adrian Nixon, you had a question regarding thermoplastics, polymers such as thermoplastics recycling. Adrian?
Yeah, I was just fiddling with my mute there, Nick. Liam, I'd heard that if graphene's mixed in with thermoplastic polymers, it can help recycling by improving the strength of the polymer. Because my understanding is, I think, does the polymer chain length start shortening the more times it's recycled? And can graphene help there?
Yeah, I can see Mike maybe wants to answer as well, but yeah, so I mean, we've certainly been working on projects. Yeah, so you're right. So generally the performance, you're going to break down the materials as part of that process, and you will get inferior properties. So we've worked with a couple of companies on a couple of projects where we've looked at maintaining some of those properties through a small addition of graphene. So it's a mixture of virgin, more recycled than you would normally be able to use, and some small amount of graphene, and able to reach sort of mechanical properties of those virgin plastics. But I can see maybe Mike wants to jump in there and make a comment.
Yeah, I think it's a really important point and an interesting one. I think what really matters is the interface between graphene and the polymer. And so you really have to choose your graphene, right? I think, to be able to get that to work. And there's going to be some polymer applications, and I think PP is probably an interesting one where that could be really beneficial, because the next option for that recycled material is going to benefit from its robustness. And then you've got things that are actually really easy to do, like PET, where we've seen, certainly in our labs, a significant decrease in performance just based on extrudability when we're following on from someone who's been using graphene in the same extruder. So it's very much application specific, but yeah, it can do that.
And I suppose as well, if you functionalize the graphene, you've got a whole other layer of complexity onto that one too. Yeah, thanks very much.
Yeah, thank you. Craig, your hand's still up. Is that for a question, or is your comment in the chat already? Briefly, because we're near the end.
Yes, it was historical. Sorry, Nick.
Okay, that's good. Thank you. I've just pointed everyone to the chat. I've sent a link. I'm going to send it again. This is a link to a survey. If you can, while we're still on this chat, if you could just click on that survey, there's about 5 or 6 questions just to fill in. And on that, you can ask for slides. You can ask for a link to the video of this webinar, and we can feedback and connect through that survey as well. So please click that link. It should take you no more than 2 minutes. While everyone's doing that, I don't think there's any more questions, are there? Let me have a quick look through. Ella Woodcock asked a question about graphene costs. I mean, that's quite an endless topic, that, Ella. What I'd suggest is feedback in the survey, and we can connect you to some of our members at the Geek who may be able to help you with material costs and things like that.
Perfect, thank you.
No worries. There's a lot about GO and water solubility. I think Bernard's handling that okay in the chat. This is an interesting one. Is there a norm or reference for testing graphene leaching out of a product? Liam, that's a tricky one, I think, but do you have a comment on that, or Mike, or what that standard should be for leaching of graphene?
I'm afraid I would assume that it's the same same standard as for other materials, but I'm afraid I don't know what that is.
That's okay. It's a tricky one.
Yeah, it's going to be changing. So right now, the EU regulations on it are awful. It should be much less. I mean, really, the leaching standards are all around plasticizers and stuff like that. And so just the aspect ratio of graphene alone is going to restrict its movement. So it should be much less. I'd be much more concerned about biodegradation or physical forces that are then doing it rather than a leaching effect. But really, people don't really understand the impact of nanoplastics themselves, let alone plastic graphene composites. Mm-hmm. It's an active area of research.
Yeah, absolutely. So I think the point to emphasize at the end again is, at the University of Manchester with the Royce, with the Geek, there's a real hub and a centre of excellence, I think, for sustainability mixed with graphene more generally, as Liam said. So please do get in touch with us through the survey, or if you're already in touch with us, drop us an email. One last reminder, just to click that link for the survey if you've not done already. It's really useful for us to get your feedback. The next webinar, public webinar, is in 2 weeks, and that's from Paul Wiper, and that's going to be focusing on CVD graphene, the challenges, the opportunities there. But you should see the links to all that on LinkedIn and Twitter and all those usual places as well. So I think we'll leave it there. Liam, anything to add at the end? Any comments to follow up on?
No, thank you all for joining. It's been very interesting.